Today's lesson we're going to cover two topics. They're both related together and all have to deal with properties of solids. So the first thing we're going to take a look at are intermolecular forces that are present in liquids and in solids. Some of you might already be familiar with some of these concepts. A little bit was covered in grade 11, and some of these things are covered in other science courses. And then we'll take a look at some properties of different types of solids and crystals and see what kind of forces are present within them and what makes them similar and what makes them different and some applications. So we're going to cover several different intermolecular forces: dipole-dipole, hydrogen bonding, ion-dipole, and London dispersion forces, and this includes some induced forces. Then we're going to take a look at some crystal structures that result: ionic, metallic, molecular, and covalent network, and look at how they're different by examining some of their intermolecular forces. So before we start with intermolecular forces, just a quick review because this is easy to get mixed up. There are inter and intramolecular forces. We spend a lot of time talking about intramolecular forces in chemistry in grade 11, and we just spent some time in grade 12. So let's do a quick overview of this again, just to make sure we know the difference before moving on. If you hear about intramolecular forces, that's RA in the spelling, these are forces that you see inside a molecule or inside an ion. So we're talking in between atoms, which means with bonds. These types of things influence the chemical properties of substances. So how reactive they are, for example, have a big contribution to intramolecular forces. So these are things like ionic bond, covalent bonds, polar covalent bonds. All of these are between two atoms or between two ions, and it relates to how electrons are shared. And part of the reason why there's differences has to do with the type of elements involved. So remember, ionic bonds are with a metal and a nonmetal, both as ions, but your covalent ones are with multiple nonmetals, and depending on how much sharing happens, you can have little sharing or a lot of sharing taking place. Intermolecular forces, again, look at the spelling here, I-N-T-E-R. It sounds similar, but it's not the same. These are forces that are exerted between molecules or ions. So between one molecule and another, or one molecule and an ion. These are different than the bonds that we saw. Those are in the molecules themselves. These are between different substances, or the same substance but different molecules of that substance. These are the things that influence physical properties: melting point, boiling point, solubility, state, etc. So the stronger the forces you have, the higher the melting point or the boiling point or the bigger effect on solubility and so on. So these are the four forces we're going to take a look at here: dipole-dipole, hydrogen bonding, ion-dipole, and London dispersion forces. So first, let's take a look at dipole-dipole forces. When we think dipole-dipole forces, remember, a dipole means you have a positive and negative end to the molecule. So if there's a dipole present, means you have a polar molecule. So if you have an overall dipole that's left on your molecule, it's a polar molecule. That's from our last lesson on molecular polarity. So if you think back to molecular polarity lesson, if the dipoles don't cancel out, you're going to have a leftover dipole somewhere in the molecule, and it creates that molecular dipole. Any type of dipole has a positive and negative end. So with a dipole-dipole interaction, it's just as simple as what the name says. The dipole of one molecule will interact with the dipole of another molecule. Or another way of putting it, we say a force of attraction with a slightly positive and slightly negative end of a polar molecule. So we don't know what this molecule is here. It's a simple two-atom molecule, but there's a dipole. Remember the positive end here means partial positive, and the tip of the arrow means partial negative. It pulls the electrons towards it. It's also shown in this diagram here why this is a little bit bigger, because it's pulling the electrons more towards the more electronegative atom. And then if we take a look and add in the charges all around, if you want for reference, you can see there's a whole bunch of partial positive and partial negative charges on this molecule. And the way that they line up, for the most part, is through electrostatic attraction, positive charge and negative charge. So you can see here in the lines in blue, they're showing attraction, positive and negative. The reds here would be a repulsion that's happening. Of course, you can't get a perfect alignment all the time of positive and negatives, but the ones in blue here, it's not a bond, but this is a dipole-dipole interaction. One dipole from one molecule interacting with a dipole from another molecule. When you have dipole-dipole forces, they can exist within a sample of the same substance. So all of the molecules are all identical and their dipoles align to attract to one another. Or you could have different dipoles from different molecules, and they can attract each other the same way. Next up, we have hydrogen bonding. This is still a type of dipole-dipole attraction, but it's one that's considered to be stronger. So we still have the same idea, two dipoles interacting with one another. It's still going to exist in polar molecules, but there's one big difference here. It has to be between a hydrogen that's attached, meaning bonded, to an oxygen, nitrogen, or fluorine. And that dipole that's created between that hydrogen and fluorine, or hydrogen and oxygen, or hydrogen and nitrogen, whatever that is, that dipole that's created between those elements will be attracted to electrons on an oxygen, a nitrogen, or a fluorine on a neighboring molecule. The oxygen, nitrogen, and fluorine on the neighboring molecule could also be part of another hydrogen bond, so one that's attached to a hydrogen itself, or it could just be to another oxygen that's not attached to a hydrogen, where you might have an oxygen with a double bond, for example. But these ones are stronger than typical dipole-dipole forces because oxygen, nitrogen, and fluorine are very electronegative, so the dipoles that form with them tend to be stronger, and they're only paired with one another, so that attractive force is higher. But one thing just to keep in mind, when we say strong, it's a strong intermolecular force. But if we were to compare it to bonding, this is our intramolecular force. Bonds between atoms, or intramolecular forces, are so much stronger than these ones. So relatively speaking, if we compared a covalent bond to a hydrogen bond attraction, the hydrogen bond attraction is only about 5% of that of the actual bond. This also helps explain solubility of water, which is covered a lot in grade 11, but you'll read a little bit more on that. Before we go on and look at an example, the other thing, hydrogen bonding, sometimes the name is misleading because you're not actually creating a bond. Think about it as a hydrogen attraction. Hydrogen bonding is just an attraction between molecules. You're not actually creating a chemical bond, just the name says bond in it. So here's a couple of examples of hydrogen bonding. So what if you had two water molecules together? You've got positive and negative charge separation. We know if we were to add in those dipoles, they point towards the oxygen. Here's that negative, here's that positive end. So this is the hydrogen bond attraction. And again, remember, it's just an example of dipole-dipole. So here's oxygen bonded to hydrogen, and it's attracted to a hydrogen that's bonded to another oxygen. You could also have hydrogen bonding happening between different molecules. So down here we've got a molecule of ammonia. So it's already drawn out for you in that trigonal pyramidal configuration. And then here's your water molecule. So again, dipoles we know point towards the oxygen in the water. For ammonia, they're going to all point towards the nitrogen there. Ammonia is polar, water is polar, they all have dipoles. And then we can see here, hydrogen's bonded to nitrogen. This hydrogen's going to be attracted to oxygen. In this case, it also happens to be bonded to a hydrogen. So you can have dipoles between two different substances that are attracted to one another, and you get that hydrogen bond attraction as well. Stronger attraction between different molecules will make things like melting point and boiling point higher because it takes more energy to pull those molecules apart to change the state. So going from a solid to a liquid or liquid to a gas and so on. Next type of force, what happens if you have a dipole that could encounter an ion? This is the type of force that happens when you look at the dissolving process. In grade 11, you would have spent some time learning about how ionic substances dissolve in water. The ions dissociate, you have a positive and negative ion, and then the polar ends of the water molecule surround those ions to keep them dissolved. That's the process of hydration. But in general, you can see ion-dipole forces happen with other things. So this one's fairly straightforward. It's a force of attraction between an ion and some kind of polar molecule. So it doesn't just have to be water, it can be any polar molecule. Remember again, polar molecule has some kind of positive and negative end because there's a dipole that doesn't cancel. So the anion, the negative ion, would be attracted to the positive end of the polar molecule. And if you had a positive ion, the cation, it would be attracted to the opposite end, the negative end. This is stronger than dipole-dipole force. And why is it stronger than dipole-dipole? When you have two dipoles interacting, they're because you have two polar molecules. And remember, the polarity part comes from the dipole itself. Only partial positive and partial negative charges. So not full charges are present, just partial. If you have an ion present, you actually have full positive and negative charges present. So you've got a bigger force of attraction because you actually have full charges involved with the ions being present. Last type of force are London dispersion forces. So these are types of forces that happen with all molecules. They can happen between any type of particle or molecule, polar, nonpolar. But if you have a nonpolar molecule, this is the predominant force for it. So something has to hold nonpolar molecules together. They don't have dipoles, so we're not going to have any of those dipole forces. So how do they have some attractive forces holding those molecules together? So there's a couple of things that can happen. One is called an instantaneous dipole. So even though it doesn't have an overall dipole present, if you took an example of a molecule, remember nonpolar means all the electrons are evenly distributed within that molecule, or we said a symmetrical distribution. Remember, electrons are constantly moving throughout orbitals when they are in chemical bonds. But imagine the electrons at one instant in time, they all just end up gathering more on one side of the molecule versus the other. So all on the orbitals, maybe let's say on the right-hand side of the molecule versus the left, just by random chance. If that happens, if you had a cluster of electrons, which is shown over here with the dots, that groups the electrons together. So what happens when you group a whole bunch of electrons together? That's going to build up negative charge. And then all of a sudden you have a molecule that looks somewhat unevenly distributed, or you could say it's an unsymmetrical or non-symmetrical molecule. What does that do? It temporarily creates a negative end to the molecule and a positive end to the other. But remember, this is temporary. So at one particular instant, it could all group there, and then the next instant, the electrons would go back and be evenly distributed. But for that one small fraction in time, you create an instantaneous dipole that kind of turns itself on and off throughout your millions and millions and millions of molecules that would be present in a sample. And just by that fact alone, you're creating some positive and negative charge, and then those dipoles will attract to one another, and then they'll allow that nonpolar molecule to stay together. A little bit more on these induced dipoles. Sometimes you can also induce a dipole to form in a nonpolar molecule. So if you imagine the same scenario, neutral species here, this would be our nonpolar molecule. Just like the last example, all the electrons are evenly distributed, which is why you see a nice sphere here, or circle, I guess, on the picture. What happens now if you had an ion that approaches? Let's say you had a positive ion. That positive ion, because it has a full positive charge, will attract the electrons in the nonpolar molecule. And for an instant in time when it's close by, it can draw a lot of the electrons towards it. And then if you look, you've got a partial negative charge and a partial positive charge that forms on that nonpolar molecule, creating that temporary or a dipole that has been induced. The same kind of thing could happen with a dipole from a polar molecule. Again, positive charge could pull in those negative charges. And again, set up the same kind of scenario here, positive and negative charge. Ions will always create a little bit of a stronger attraction versus dipoles would be weaker, just because this is a full charge, and remember these are partial positive charges. So let's just summarize what we've got here in terms of strength. So summary for intramolecular forces, the hydrogen bonding attraction is the strongest, followed by ion-dipole, then dipole-dipole, and down here London are the weakest. Sometimes you might also hear this combination of forces referred to as van der Waals. That's often used a lot in biology. These are the same types of things we're talking about. Now what we'll do is put a few of those concepts together with intermolecular forces and have a look at some solids that form and some differences between them. So first are your ionic crystals. We spend a lot of time talking about ionic compounds in grade 11. So a lot of these things should sound familiar to you with a little bit new added in. So remember, ionic crystals, they're solids, they form different crystal structures, they're white, they have high melting points, high boiling points. That's because of the repeating patterns of positive and negative ions attracted to one another in the crystal structure. The crystal structure we refer to in chemistry and science as a crystal lattice. That's because with ionic crystals, you have a series of positive and negative ions that are attracting one another, and they create different crystal shapes. So one that you're familiar with is sodium chloride, table salt. And if you look closely at grains of table salt, you'll see that their crystal shape takes on a cubic shape. But there are other shapes that can result, like an octahedron shape and others, depending on what ions are there and how they pack together with one another. If you go on and take a look at more chemistry beyond high school and do look at more solids, you'll learn more about different ionic crystals and arrangements, and there's different names for them depending on how the different ions interact. So just to show you some contrast, because we're always used to seeing table salt being used and making that regular cubic shape, these are some other arrangements you could see when you're looking at crystals. And you can investigate this further on your own if you're interested. There's simple cubic ones. There's ones called body-centered cubic, which would change the shape a little bit. Face-centered cubic. Depending on what ions are involved in their sizes and their charges, they pack together differently. Next type of solid are metals, which we call metallic crystals. So when we think about metals, we think about some of their properties. We know they tend to be solid at room temperature, except for mercury. They tend to conduct electricity to varying abilities. Some metals are better conductors than others. Some can be hard, some can be soft, depending on which metals you're looking at. But one thing that's common with most metals is they have a low electronegativity. So remember, electronegativity measures how much an atom wants electrons when it's forming a chemical bond. We know metals have low electronegativity, meaning they don't really hold on to their electrons strongly. And remember, they also form positive ions when they do bond with something else. So, because of this property, metals don't hold on to their electrons very tightly. And when you find a pure sample of metal, what ends up happening is the electrons are actually held very loosely and tend to be a little bit mobile. Mobile meaning they can move around a little bit more freely maybe than, say, ones with a non-metal. When you have a whole bunch of metals arranged in a solid structure or a metallic crystal, the electrons can move freely in and around all of those metal atoms. Because they move, the metal atoms will have a slightly positive charge to them, and then it keeps all the electrons around them. And this allows for conductivity to happen. So if the electrons were held on too tightly and weren't able to freely move throughout, they wouldn't be able to pass through, let's say, a copper wire that's used for electrical wiring. So the electrons stay and are shared amongst all of those atoms, but they're moving. The way that they describe this in a lot of models of metallic crystals, they say the electrons are delocalized or they're moving around, or you could say that the electrons create kind of a sea surrounding all of those positive metal cations. One other type of crystal you will see we refer to as molecular crystals. Molecular crystals are the ones that are nonpolar. So non-polar crystals, no dipoles, so you have no dipole-dipole forces or anything else like that. Because of that, the only type of forces that hold them together are London forces, those London dispersion forces, and we know those are the weakest ones out of all of them. So when you look at molecular crystals and their properties, they're going to be different than, let's say, an ionic compound. Molecular crystals, they can be solid, but maybe they're not going to be as hard as the ionic ones, or their melting and boiling points are going to be lower because the forces holding those ions together are a lot weaker. One that you may be familiar with is iodine. If we look at its general structure, it's made up of a whole bunch of different diatomic molecules, all attracted to one another, and this is what its crystal structure looks like. It's hard to tell from the picture, because we can't touch it, but this type of crystal is very soft. So it forms crystal, but it's very irregular. There's not much of a pattern here. And if you're able to touch it, it crushes very easily. Another example could also be sulfur. And if you have time to Google this, you could Google sulfur crystals. We know sulfur is that rotten egg smell, but it has a nice yellow crystal structure. But again, it's also very brittle and very soft and can be crushed into powder very easily. So you could also take a look at that one if you're looking for another visual example. Finally, we have a special class of covalent molecules that form a unique type of crystal. They're called covalent network crystals. There's different types of covalent network crystals, and with your homework, you'll read about a few different ones. But in general, what makes these ones different is when you look at the covalent bonds in these crystals, their 3D arrangement is special. And it extends in kind of a repeating pattern throughout the whole crystal. And this makes the atoms held together by very, very, very strong covalent bonds that have some kind of direction to them. These are stronger than most other types of crystals that are there. As an example of covalent network crystals and looking at some different ones, we're going to take a look at some carbon-based network solids. There are other types of covalent network solids, so make sure you read through in your homework and make note of a few others. We're going to focus on these ones. So if we're looking at an example with carbon-based network solids, we know bonds between carbon and carbon. These are covalent bonds. So all of these molecules are all made up of carbon bonded to carbon, but in 3D they're arranged in a few different ways. All of these crystals we call are allotropes of carbon. Allotrope means they're different three-dimensional or crystalline structures of the same element, but their physical and chemical properties will be different because that arrangement between the bonds is different. So these are a few that we're going to take a look at next. Diamond, graphite, and a few different nanoscience applications with Buckminster fullerenes and nanotubes. So first, let's take a look at diamond. Diamond, we know, is one of the hardest substances on the planet. It's made up of carbon. It's not a good conductor, but it's very strong. So what happens? All of the carbons in diamond are bonded to 4 other carbons. If we take a look, carbon in the center with 4 bonds around it, guess what? It's going to take on tetrahedral shape. Every single carbon in diamond has a tetrahedral shape and arrangement, and then all of these are bonded to other carbons, and they have tetrahedral arrangements, and it makes this network of tetrahedral bonds all around that's very organized, but it makes it very hard to make a clean cut or break throughout the structure. What happens if we look at another example, graphite? Graphite is also made up only of carbon, but this time, when we look at the carbons, each carbon in graphite is bonded to 3 other carbons. This carbon here takes on a trigonal planar shape. Now you might be thinking, well, carbon has 4 electrons around it. What happens to the other one? The other 1 electron that's not paired with anything sits in between these sheets of graphite. So trigonal planar shape, remember, means flat. All of the carbons are bonded to 3 other carbons. It's going to create some sheets, flat sheets, and then those electrons that aren't paired with anything are going to be found in between the sheets. They might find a partner from a neighboring atom, but the electrons are more loose or freely flowing. If you know anything about graphite, graphite is a good conductor. It has a high melting point, but it's soft. And the reason why it's soft is when you use graphite, single sheets come off one at a time. Or think about when you're writing with your pencil, they used to use some graphite in there. The graphite comes off one layer at a time, or if you're pushing hard, several layers at a time. Then we have a few cool, interesting applications of carbon network solids. So one is called a Buckminster fullerene, or it's commonly named a buckyball. And this one, we're taking carbon and we're bonding it to three other carbons, but then we're arranging it in a ball shape. But this shape isn't flat here like trigonoplanar, it's more like a trigonal pyramidal shape. But I wouldn't call it a true trigonal pyramidal because the bond angles between the carbons here wouldn't exactly be 109.5 here, because when they're arranged in this ball, they kind of bend and shape differently. But these types of buckyballs are being tested out in trials right now with cancer medication. They can put cancer medication inside these balls, put a little tag on the outside that tells the ball where to go in the body, or it might signal something in the body, and then those cancer medications can be delivered to a certain part in your body for treatment. Other one, what if you're dealing with a nanotube? You might have heard of nanotubes. Again, this is where carbon is bonded to three other carbons, but it's stretched into a tube. And this one again takes more similar to the trigonal pyramidal shape, but again, the bond angles aren't exactly true trigonal pyramidals, so I wouldn't want to say it's a true trigonal pyramidal shape. But a lot of work's going into these nanotubes in making high strength fibers for used in engineering. They've been used in bulletproof vest and other armor. So it's another cool application of these crystal structures. A couple of these areas might be something you might consider if you're doing some research on nanoscience. They might give you some ideas of where to start. So let's take a look at a summary of all of the types of crystals. There's also another chart that's posted up in the notes that you can take a look at as well if you want to print off a kind of study sheet. So we've got our four types of crystals. What types of particles are there? So we know ionic are positive and negative. Metallic have those positive cations. Molecular are just molecule. And we have covalent network, which are atoms. We have different types of forces that can be present between them, and then different properties. This is kind of like a review of some properties in grade 11 and some other examples. So that's our lesson on both intermolecular forces and reviewing some different types of solids and crystals.